Okay, limits and continuity, part 2. This is lesson 2 of the Calc A review. Go ahead and move down to second page here. All right, so last time we talked about evaluating limits. It's pretty easy to do analytically if you have a continuous function. We started talking about what to do if you have a non-continuous function. Specifically, we had said if you have a point discontinuity, you're going to do some factoring, and after factoring and canceling, you should be able to evaluate the limit similarly to continuous functions. So today we need to talk about what to do with what's called a non-removable discontinuity. So you have a function that's not continuous, and there's not a way to factor out from your equation to simplify a function. Okay. If we can neither plug in nor factor to evaluate, there's probably a vertical asymptote. That's the first thing to realize. There's probably an asymptote in the graph at the location where you have your discontinuity. At a vertical asymptote, the limit is going to be one of these three results. Either you're going to say the function goes to infinity, it goes to negative infinity, or perhaps we say it does not exist. To figure out which of those is correct, you do have to consider what's happening from both the left and right sides. Example 2.1, for each function, consider what the graph will look like. This is where it becomes really important that you have your algebra fundamentals down. If we see a function such as x minus 4 over x plus 3, it is expected that you can get a rough sketch of that even without calculator help. I would say, use a calculator for now if necessary to check, but there are ways to get a pretty decent sketch of this without a calculator. First and foremost, we know that x equaling -3 is a problem in the denominator because that's where the denominator would go to 0. And that x plus 3 is not cancelable with anything in the numerator. So that right there is how we know there's an asymptote at -3, which you can see I drew that in my sketch. You might also notice my sketch has what appears to be a horizontal asymptote, and those are actually also pretty easy to identify if you think about how your function behaves as you approach infinity or negative infinity. So I'm actually thinking of a limit of this function as x gets really, really big. And of course, because the lead terms, top and bottom, have the same degree, we just look at the coefficients. Basically, I'm allowed to ignore the -4 and the +3 as I go to infinity. I'm only worried about how x over x behaves, and x over x just turns into 1. All right, so I've got my sketch. As you approach a vertical asymptote, a function is always going to either get super, super big or super, super negative. And to figure out which is happening, it's just a matter of plugging in or imagining plugging in numbers very close to your asymptote on either side. So as I come in from the left towards -3, you might imagine plugging in -3.1 or -3.01 or -3.001 into this function. And really, you don't have to evaluate that to get the actual numerical answer. You just need to process it enough to know, is it going to come out to be negative or positive? If I were to plug -3.1 into this thing here, both the numerator and denominator would come out to be negative, which means the overall value of that function is positive, which means I must be approaching a positive infinity. Likewise, coming in from the right side, okay, how did I know to draw the graph the way I've drawn it here? Well, if you imagine plugging in -2.9 or other numbers really close to -3 from the right, you'll soon realize that the values of this function are going to be negative. Therefore, we must be approaching a negative infinity. Now, having established the left and right side results, next I'm looking to see, do they match each other? And of course, it's different flavors of infinity. So my final answer for the overall limit approaching -3 does not exist because I'm not getting the same result from both sides. Go ahead and work through the other example on this page if you like. I'm not going to necessarily talk through it, but I do have the answers here for you to check as you go. Example 2.2 on the next page has this kind of mixing and matching different types of discontinuities. What types are present? Whoops, excuse me. What types are present, and then evaluate the limits. With this f of x, shown first. We see there's an issue at -2. There's going to be discontinuity, but this is a point discontinuity. We see something that's factorable and cancelable. So of course you would cancel those out, and a limit to -2 would just be plugging in -2 into whatever's left. Limit as x goes to 1. Well, this one's even easier because we don't have a discontinuity at x equals 1. So you can just plug the 1 directly into all of that stuff there to get back a 0. The y of x down below has two different discontinuities. You'll note in the denominator there are two different x values that would turn the denominator into a 0. And yet they're different flavors. One of them is a point discontinuity. I see cancellation there. One of them is infinite. So this function, if you graphed it, would have an asymptote, but also a single point discontinuity. All right, that's about all we're gonna do with those types of discontinuities for now. We're gonna transition a little bit here. What's happening at the rest of the page is getting into another topic. Now we're gonna start delving more into limits as x approaches infinity or possibly negative infinity, instead of, x approaching a finite number that we can identify. So this is equivalent to saying what happens to my function if x gets really, really big or really, really negative. Another name for this process is analyzing end behavior of a function. And as you surely know, some functions get super, super big as x gets big. Some get super, super small. Some functions might actually approach a finite value. Those are the ones that have a horizontal asymptote. All right. As x gets really, really big, some terms within a function will grow so much faster than others that they essentially control the value of the function. They render the other terms negligible to the point you can disregard them. So a lot of this process revolves around identifying what's the strongest term of the function, and then looking at what that term is going to do as x gets really big. Okay. Let's look at some examples. 2.3. End behavior of polynomials. You only need to look at the highest degree term. Everything else becomes negligible. So for part A, what happens as x gets really big? All I really care about is x to the third. That is the most powerful term here. So I can effectively ignore everything else and just observe that as I plug really big numbers into x cubed, you're going to get back even bigger results. So naturally, we say that limit goes to infinity. Part B, same function, but this time we're approaching negative infinity. Well, if I start plugging larger and larger negative numbers, -100, -1,000, -1,000,000 into x to the third, I get back a very, I should say a negative number with a high magnitude, right? So we say negative infinity. Part C, x going to positive infinity, but you do have to consider any coefficients in front of your strongest term. So I'm looking at the x to the fifth term, but because it's multiplied by -2, my final result is negative infinity. Likewise for part D, x approaching negative infinity, if those really negative numbers are getting squared, they are going to turn positive. Okay, so that's generally pretty simple with polynomials. What's a little more interesting are what we call rational functions. Rational as in ratio, as in fractions. So talking about functions that look like maybe a polynomial over another polynomial. You can see examples down below. These are a little more complicated, but still not too bad. You do have to consider three different cases. The first case, again, you're looking for the highest degree term or terms within the entire fractional function. If that highest degree term lives in the denominator, that means the denominator is going to outgrow the numerator. And of course, in a fraction, if the denominator is super big compared to the top, you're getting results that are close to 0. So naturally, we would say the limit of these functions as x gets big is 0. And you can also then conclude that there's a horizontal asymptote at y equals 0. Now, flipping that around, if the highest degree is in the numerator, that means the top of the fraction is outgrowing the bottom. And when you have fractions with numerators that are way bigger than the denominator, then the overall value of the number is big. So these are the ones that are going to go either to infinity or negative infinity. You do have to look at the sign on the strongest term in the top, but also the sign on the or in the denominator of the fraction, because even though that denominator might be negligible in size, it still contributes a sign to your answer. The third case, if you have equally high degree in the numerator and denominator, then neither part of the ratio outgrows the other. So instead of going to infinity or 0, you have your ratio approaching some other constant finite value. All right. So the limit equals, in this case, just the ratio of the coefficients on those strongest terms, top and bottom. And that also, again, indicates a horizontal asymptote. Let's look at some examples. As you can see, actually, the entire first row of examples here are ones where the strongest term lived in the denominator. That's why all those answers evaluate to 0. Be careful in something like B. The terms aren't guaranteed to always be in order based on degree. So this negative x to the third at the end there is the strongest term. The next row, you'll notice that the strongest term is always in the numerator. So in part D, I'm looking at that 3x cubed. If I plug really big numbers in there, I get back really big numbers. The sign in the denominator also would remain positive, so I'm safe to put an answer of positive infinity. E is the same function, but this time to negative infinity. Okay, so now I'm plugging really, really negative numbers into 3x to the third. That goes to negative infinity. The sign is not flipped by the denominator at all. Choice F. X goes to negative infinity. We're cubing that. It's still negative, but then you do have to consider the extra negative sign on there that flips it back to positive. G is an interesting one because x is getting big. X squared is the most powerful term. So the numerator reads as big positive numbers. But even though that's the case, the denominator is going to contribute a negative sign based on this negative 3x being the most powerful term in the denominator. So you do have to be careful there. The answer would be negative infinity, thanks to this little negative sign right there. H and I, these are the ones where if you look real closely, you'll see that the highest degree term is in both the top and the bottom. We've got x squareds in both places. In that case, you look at the ratio on those terms, 7x squared over negative 4x squared. I've got a horizontal asymptote at or I should say y equals negative 7/4. So that's my limit. Likewise here for I, it doesn't even matter if you're approaching negative or positive infinity. We can still just look at the ratio of those coefficients. The answer there is 5. Few important facts. Just informally, I hope you have a decent sense of growth rates of different types of functions from algebra. As x gets really, really big, log functions, they do increase infinitely, but they grow very slowly compared to a lot of other common functions. If you're not familiar with the graph of a log functions, that's something you should look at. It comes up quite a bit in this course. Polynomial functions do grow faster. Exponential functions even faster than that. This exclamation point stands for factorial. X factorial, that means you're taking a given whole number and multiplying it by all the subsequent whole numbers counting down to 1. So for example, 4 factorial means 4 times 3 times 2 times 1. But that type of progression actually grows really quickly. It grows even faster than exponentials. And the grand champion is x to the x. That one grows super, super fast. I've got another limit for you that for now, it's probably in your best interest to memorize, although intuitively, this one's easy to figure out. Sine functions oscillate between -1 and 1. So this numerator doesn't really grow at all. Whereas when x increases, the denominator is going to get bigger, 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 bigger. So this ratio is going to approach 0. This is not exactly the same limit we saw in the previous lesson, but it is similar. Okay, example 2.5. Here we see some slightly more complicated functions, and you're tasked with finding any horizontal asymptotes. And again, the strategy for horizontal asymptotes in this class is always just automatically set up limits, but you want to check both infinity and negative infinity. All right. Looking at example A here, as x gets really, really big, you can essentially ignore these absolute value bars because x is going to be positive anyway. So in that case, we're essentially looking at 2x over x, which gives me a ratio of 2. If you go to negative infinity, however, the x in the numerator is going to make 2x into negative numbers, whereas absolute value of x, of course, remains positive. So you've got a different sign top and bottom. You have to be careful there. That means if you move really far to the left, if you graph that function, you would eventually see a horizontal flattening out at y equals -2. B is another tricky one. It's tricky because this square root kind of freaks us out. But again, the square root of 16x to the 6 would just be 4x cubed. And as we go towards infinity or negative infinity, the +1 is negligible, so you can basically ignore it. So the way to interpret this is you essentially have a 2x cubed plus a 4x cubed, which would make 6x cubed. And if you imagine having a 6x cubed there, well, that's how we know that we're going towards 1/2. You got 3x cubed from the top, you've got 6x cubed on the bottom. Going to negative infinity, we just have to be careful because the 2x cubed reads as negative. The radical still reads as a positive 4x cubed. So you got -2 plus 4 gives you 2x cubed in the bottom. And then you have, again, a negative term on top. So overall, you end up with a -3/2 if you look at the ratio of coefficients. C, this one's weird because we've got an exponential term in there, and those do grow really, really quickly. So as I go to infinity, the strongest term is the -5e to the x. So, and the fact that it's negative leads me to a conclusion of negative infinity. What's interesting is as x gets really negative, e to the x is no longer super powerful because e to the -100, e to the -1000, e to negative powers, that is approaching 0. So that term disappears when we go the other direction, in which case it's the 2x squared over 7x squared that we're looking at as the strongest terms. All right, the rest of this video, we will get back into continuity, talk about some of the properties there. Informally, we've mentioned already that it's a function, well, a function is continuous when there are no breaks. Here we see a function that's continuous in a lot of places, but also has some discontinuities. So here's the domain. You can double check that on your own. However, domain and continuity aren't exactly the same thing. We can be defined at certain locations without actually being continuous. Like at 1, for example, the function's defined. There's just a hole at this single point off by itself there. Same at the jump here. Function's defined at -2, but we're not continuous. So my interval for continuity is a little different than my interval for the domain. Now let's get into the formal definition of continuity. Informally, we understand what these things look like, but what is the actual calculus definition? Okay, and it has to do with limits. Essentially, we can say we're continuous at a point if the limit of a function as we approach that point is the same as what's actually defined on the function. Or in other words, the location that we're approaching is the location that we actually do end up hitting on the function. Okay. So you lose continuity 3 different ways. You would lose continuity if both of these sides of the equation are defined, but they just aren't equal to each other. Or secondly, you might lose continuity if the limit just does not exist, because you can't say a limit's equal to f of c if the limit doesn't even exist. And thirdly, if the function value itself does not exist, if there's an open circle with no filled in hole, that would violate continuity as well. All right, so using the definition, we're kind of explaining why we lose continuity at these specific locations in the graph pictured at x equals -2. The issue is that your limit does not exist because you're not approaching the same y value from both sides. Okay, at x equals -1, there's not even a defined value on the function. You have an asymptote, there's nothing there. So f of -1 just does not exist. And then finally at x equals 1, the limit exists, the function exists, they're just not the same value. Okay. Types of discontinuities. There's 3 types that you could observe in graphs pretty easily. They call jump, infinite, and point. Jump is where the curve stops and picks up somewhere else, just like what's happening at -2. Infinite just means asymptote. Your function's approaching either infinity or negative infinity from one or both sides. And then, of course, the point or removable discontinuity is when you have just a single point that's not connected to the rest of the curve. All right. Moving on, I think this is the end here. Last concept, we'll just touch on really quickly a theorem that you saw in Calc A that's related to continuity. It's called intermediate value theorem. This basically just says for any function that's continuous on a certain interval, like here we see a function that stretches from x equals a to x equals b, and it's continuous, then whatever y value you started at, whatever y value you end at, somewhere within that interval, you're going to hit all the y values in between, possibly more than once, but each y value from f of a up to f of b gets traveled through at least one time. And then I have a quick little example that you can look at that uses that theorem to prove that if you hike a certain trail one day and then you hike it the next day, there's going to be, and that's across the same time intervals, there's going to be at least one point where you're at the exact same point on one day as you are the next day. All right, so that concludes the video. Let me know via questions in class or an email if you have any questions about what you saw. Thanks.